So my name is Kirsten, for those who don't know me yet. And I will be presenting the first part of Work Package 5. And the goal of this part of the work package was to explore 3D printing in combination with high precision instruments, such as those used in eye surgery. And I will quickly go through the results of how we obtained a 3D printed functional trocar for eye surgery. But if you need some more background information, I refer to the publication, for which the link is here. Okay, I will start with explaining a bit more about eye surgery. So in eye surgery, there's two areas of the eye that are relevant. The first is the anterior section, which is everything from the front of the eye up to and including the lens. And the second part is the posterior section, which is everything from behind the lens to the back of the eye. And this is the part of the eye that we're talking about in this work package. So in posterior eye surgery, it's often necessary to get access to the retina, which is the outer layer of the eye, in the back of the eye. So for the surgeon to have access to that part, he needs to go from the front of the eye and cross all the way to the back with the instruments. And in order to do that with as little damage as possible, they place a number of trocars, which are temporary ports into the eye that remain there for the duration of the surgery, and they can be used to exchange the instruments through. So this is a typical setup for eye surgery that you see here. There's usually 3 trocars that are placed during this type of surgery. And in eye surgery, the trocars consist of a cannula, which is the actual portal into the eye, so that's placed inside the eye in the sclera. And then the valve, which is placed on top and it remains outside of the eye. And this has the function of preventing any fluids or gases from escaping from the eye. And here below in the photo, you can see the actual size of a trocar. That's not 3D printed. This is the actual one from Tork. So it's quite small and it has an internal lumen of 0.4 millimeters. So the goal of this work package was to 3D print this functioning trocar. And we did it by first analyzing which 3D print method would be suitable for that. And we chose stereolithography or SLA printing. In this print technology, we have a photopolymeric resin that's cured by means of a laser source. And then typical post-processing steps are cleaning it with alcohol and curing it with UV and heat radiation. So the advantages of this method are that you can obtain a relatively high resolution of 25 micron. Also that the build volume is relatively large as compared to, for instance, nano 3D printing methods. And finally, we also have biocompatible materials available and what's relatively cheap to use. So in order to 3D print a trocar, first we drew up some requirements. So for the cannula, it is important that it's made of a rigid material, so it doesn't break when it's inserted into the eye. But also it needs to be compatible with industry standard instruments so that they can be inserted through it. And for the valve, it's important that it's made of a flexible material so that it has compliancy to let an instrument enter the eye. But then also it needs to be able to close after the instrument is removed. And when there's no instrument inside, there can be no open gaps because otherwise it wouldn't be able to prevent any leakage. And since the requirements for both of these parts are very different, we decided to print them separately from each other. So I will start by explaining more about the cannula. First, we didn't change anything to the design of the cannula, so we printed it as is. And we evaluated 4 different materials that are available for SLA printing in 3 different print orientations and 3 different layer heights, just to see which would lead to the most accurate results. And here you see a photo of one of the samples. So there's 9 cannulas that are in different print orientations, and everything that's below that is the support material that still needs to be removed. Well, they look okay if you look at them from a distance, but then when we look with the microscope to the distal ends of the cannulas, we see that they're actually all fused shut. And even the one that looks like it has potential, turns out that it wasn't even printed correctly. So these results, yeah, they were regardless of material, print orientation, or layer height. So from this, we actually concluded that it's not really possible to print the design as is and that we need to make some changes to it. which we did. And this shows a comparison between the old design and the new design. And I will explain why it looks the way it does. So in the old design that you see on the left, if you look at the cross section of the surface area that needs to be printed for each layer, it's always the same. So it's always a circle that is stacked on top of each other. But because of the laser source of this type of printing technology, there's a bit of scattering and diffraction of the laser that happens, which means that it partially also cures the surrounding area that's highlighted in light blue there. And because it's the same surface area for each layer, this means that the cumulative effect of this, this false printing that kind of happens surrounding the laser spot will completely fuse the internal lumen of the cannula. So in the new design, which has a helical shape, the surface area for each layer changes a little bit the location of where it needs to be printed. And because of that, this same effect that occurs doesn't have the opportunity to build up and fuse the entire thing. And underneath the microscope, that looks like this. So here we experimented with different number of revolutions for the helix. So you can see all the way on the left that there's a very open structure, and it's very clear that you can see the helix. But when we increase the number of revolutions, at the end, we reach a completely closed tube. And this is what it looks like a little bit more zoomed out. So here you can see the 3D printed cannula. You can still very clearly see the lines of the helix, but it's also open, and we were able to insert a 0.4 millimeter trocar knife into it. We did the same for the valve. So first, we tried to 3D print the design of the valve as is. Again with 4 materials, this time also 2 flexible materials. And instead of changing the print settings, here we changed the top thickness and the thickness of the slits, because we want the slits to be printed together as close as possible without any open gaps. But again, the results for the first trials were not great. So either we have slits that are very opened up, or there's only a hole in the center, or they're completely fused shut, basically. And also not all the materials were suitable. So for some of the materials, when we inserted an instrument, instead of opening up, they just break, as you can see here. So this is not possible to use, which is also why we made a design change to the valve. And in this case, we opened up the flaps of the valves to the outside. So they're pointed now under an angle upwards, which creates a bit more space around each of the valve flaps, allowing them to be printed without being fused shut because of this false printing effect. And after printing, we place them in an enclosure that presses the valve flaps down to their closed position, and then we cure it. And after curing and getting it out of this enclosure, the valve flaps remain in the closed position, as you can see here. And this we tried with a flexible material, which you can see the results here. So you can see that it's possible to insert the instrument and remove it, and the valve flaps really close nicely without any gaps after removing the instrument. So with these 2 parts printed, we were able to create a full trocar. You can see it here in comparison to the existing Dork trocar. You can see that the wall thickness of the cannula is a bit thicker, but it has the same internal lumen. So both have an internal lumen of 0.4 millimeters. And this trocar we evaluated in a pig's eye, which I have a movie of now, so if you don't want to see it, then I suggest you look away. So we were able to insert this trocar using a 2-step incision. So first we made an incision with a separate knife, and then we were able to insert the cannula, or the trocar, which was necessary because of the slightly larger wall thickness of this 3D printed trocar. But it's, as you can see, possible to insert, and we were also able to retract it out of the eye without it breaking. So in conclusion, that means that we were able to 3D print a successful trocar that at least falls within the size ranges of eye surgical instruments. It's possible to insert and retract without breaking, which is a good thing. And yeah, even though it's not necessarily a better functioning trocar than the one that already exists, it does open up the possibilities of using, for instance, a personalized trocar that can be adjusted to the specifications of the eye of the patient, or to a specific function. So for instance, to make it compatible only with one type of eye surgical instrument. And that was, for me, the part of the trocar. So now I think I can give the floor to Marta. Thank you. Don't look at the screen. Okay.
Take your sweets with you.
Oh, yeah, then I think you can have questions at the end. Not all on me. Anyway, hi, I'm Marta Scali. I work at the Dutch Ophthalmic Research Center, and before I was a PhD at TU Delft. So for me, it was also a nice opportunity to collaborate again with TU Delft, this project. Now I'm going to talk to you about a second activity that we did within this work package. And the goal here was to develop a design, 3D printed design of a mechanism of a vitrectomy out of a single part without the need of assembly. So in this way, we could also look at other possibilities of how we could 3D print other possible instrument, non-assembly, without assembly steps for other medical activities. But we chose eye surgery because it has more complex and difficult design to actually print. So that was why we were also involved in this project. So to link a bit on what Kristen already mentioned before, we are in the back side of the eye, so the vitrectomy is also an instrument used for posterior eye surgery. Actually, this is how it looks, and then the instrument is used for the procedure that's called vitrectomy. That is a surgery used for remove some or all the vitreous humor from the eye. And the vitrectomy cuts the vitreous in small parts, and then you can aspirate through the same instrument all the vitreous outside of the eye. And it is connected to a machine, which also gives the input for the actuation of the instrument and for the aspiration of the vitreous. Now here with this video, you can actually see better how it works. So we have two knives, how we call them, the outside and the inside knife. And the inner knife, it's moving very fast. Now here you see slow, and soon it's gonna speed up. And by doing this motion, you have a cutting effect of the vitreous, and then it is aspirated via the tube. And this goes a very fast cut per minute, basically, that's how we call it, fast 8,000 cuts per minute. And this was also one of the functionalities that we were looking for in a 3D printed vitrectomy. Now, if you look at the mechanism, it's quite complex. It's made out of many parts. And this instrument is actually assembled all by hand. So all these parts are manually assembled, which takes also a lot of time. And it is a challenge to actually print it in one step, if you look at this in this way with all these parts. So first we thought, okay, we have to rethink the design and make it in a way that is also printable. So what we did is we made a different type of design, which has little parts. In this way, you see we use a dual diaphragm design, and the mechanism, how it works is the same as the previous one, but with little parts. So we have the same effect. So we have a diaphragm used for sealing and another diaphragm used for actuating the inner knife back and forth. So we will have at the end the same effect as the actual vitrectomy, but with less parts. So this, in theory, is more feasible for a 3D printed vitrectomy. And that's what we try to do. And thanks to our partners in the project, we managed to actually print this with what is known as PolyJet multi-material 3D printing. So we use different materials in one print, and we could print both flexible material for the diaphragm and the rigid material for the carrier of the knives inside and the body outside, which has to be rigid. So the diaphragm were made with different percentage of flexible and rigid material, so that you can have different stiffnesses of the diaphragm going from flexible to more rigid. And this is how, in a simulation, you can see how it should work at the end, the prototype. So as you can see here, it doesn't look exactly as a vitrectomy. We decided to make it as a test prototype, so they would be able to actually put it into a test setup and test it. And that's what we did. We test first for spring force and also for speed. And as you can maybe barely see here, because it's quite a small movement and also very slow. as you can see in the movie on the, yeah, it's moving, but it's very tiny, so you probably barely see it. And this was indeed, well, we were happy that it actually works, because that was the first challenge, being able to print it and let it work. So it works, but the functionality of the speed that we wanted to achieve is still not there. So that requirement we still didn't manage to meet. So we decided to look at different aspects on why this was not possible. So one is material properties, because we know that we are using different percentages of materials, and they can go from flexible to rigid, more rigid, and then all these are anyway a bit flexible, and they all have what we call hysteresis. So when you load the material and unload, it doesn't behave in the same way, and you have loss of energy, and the material doesn't go back to the same to the start position. So, and this happens very slow also. So we have to find a way to solve this, but we know that with 3D printing at the moment we can use only polymers, and that's what we didn't know how to solve this problem. So at first we said, okay, let's focus on, we know there is hysteresis, let's see how much it is, and maybe what we could do instead of solving the problem is to compensate for this problem. So if we have hysteresis, we know about it, we can quantify it, and then we can compensate in the design of the Vitrectum for this. Also, we look into how we can improve the design even better. So we added, for example, a flat spring that helps with the movement of the backward motion, knowing that also the spring has less hysteresis than the material itself. So you can add a spring to the diaphragm, and in this way we could actually help the diaphragm to move backwards faster. However, this help was not enough to get to 8,000 cuts per minute. So we managed to make it a bit better, but not as better as the actual Vitrectum that we wanted to have. But if we look at the big picture, the challenge was already quite big, because we started for a very complex design, and we managed to simplify it by using a different completely design that is the actual mechanism of the Vitrectum. So we use a dual diaphragm design that could be able to, that we could manage to 3D print without assembly steps, thanks to the PolyJet printing technique. And then we managed to test these prototypes with applied pressure, and we managed to get the spring force that we wanted. Unfortunately, not the speed that we wanted, but one step at a time. And then we investigated more about this mechanism. So instead of going full on and test it only this type of design, we started to understand more about it. So we understand about material properties, with knowledge of hysteresis of the material, and also knowing what are other opportunities or possibilities in the design to improve it in the future. And then, of course, the next step will be to make it as a full instrument. At the moment, it's only a mechanism, but that was the main challenge, and we only focused on that first. And then the next also step, once this mechanism will work, is also to make it work in ex vivo, like showed before by Kristen with the trocar. Trocar is more like a passive instrument, and this is more an active instrument. So that was the extra challenge that we faced in this part of the project. So the next steps, unfortunately not in the project because it's finished, but hopefully in the next follow-up project, could be to look at other materials that have no hysteresis, for example, metal, and with the improvement of 3D printing techniques, that could be also possible probably in the future. And this is a possible design of a different diaphragm that you could think about, and different actuation mechanism also. Now we chose the dual diaphragm, but there are also other options that we described in the deliverables. For whoever is more interested, we have other options. We only had to choose one for this project, and this is our choice. But overall, we were really happy because, yeah, we managed to let it work. Of course, not as good as the Vitrectum, but the Vitrectum has many years of development than just 4 years. So, and yeah, so this was the end. But I wanted to really have few seconds of thank Kristen for the collaboration that I had with her all the time. Also, G and Amir for the support, and Oceans and 3D Life Print for the nice brainstorming sessions we had and helped with prototyping and still helping also after the project finished. So it's really nice. Thanks.